Alright everyone, welcome to my very first video, and for our first lesson we will be doing some physics. And today we're going to be looking at cosmology, which is chapter 28. But before we dive into the lesson, let's take a look at the specification. So we are covering part D of the astrophysics session, and as you can see we have the content written in bold and we have a P after the spec points, meaning that the entire topic, cosmology, will only be assessed on paper 2. So you do not need to revise this for paper 1, and this is only for triple science students who are sitting for 4PH1 specification. So cosmology, the word, it actually comes from the noun cosmos. Now cosmos means the universe. So cosmology is essentially the study of the universe. And at international GCSE level, the thing that we're interested in with cosmology is we're interested in looking at the origin and evolution of the universe. So how it started and how it's changed over the years. And the most dominant theory that explains the origin and the evolution of the universe is the Big Bang theory. And this is the theory that you need to know really well for your 4PH1 examination. Now, the Big Bang theory it essentially states that the universe began from a single, infinitely hot and dense point. And from that point, it rapidly expanded and it created everything in the universe. And since the Big Bang, the universe has been expanding and it has been cooling down. So that's what the Big Bang theory states. Remember, it's a theory. But this theory has two pieces of evidence that back it up. So these are two pieces of evidence that you need to know for your international GCSEs. The first one is cosmological redshift, and the second one is cosmic microwave background radiation, or CMBR for short. And do remember that these are very frequent questions, so make sure that you do know and you do understand this topic really well, because if you get it, then you can easily bank 10 to 12 marks on your paper 2, which will really push your mark to that grade 9 that you're looking for. So first, let's take a look at cosmological redshift. Now, before we look at the cosmological redshift, you need to know a little bit about this guy, and this guy is Edwin Hubble. Now, he likes to look at galaxies using a telescope, and one day he was measuring the wavelength of light from distant galaxies, and he would also measure the reference wavelength. So the reference wavelength is essentially the wavelength of light that is emitted in the laboratory on Earth. So it essentially represents the wavelength of light that would be when it were initially emitted from those distant galaxies that he were looking at. And what he found was that the wavelength of light that he receives on Earth is greater than the reference wavelength. So the wavelength that was initially emitted from the stars has actually increased, right? And if you remember chapter 3, waves, and if you recall the Doppler effect, well then you would know that an increase in wavelength occurs when a source of a wave, like an electromagnetic wave or a sound wave, when that source moves away from the observer. And so from this observation, we can conclude that because the wavelength of light emitted has increased, the galaxy from which that wave comes, well, that galaxy must be moving away from Earth, which would cause the wavelength of light to increase. And so Hubble did this for a bunch of different distant galaxies. And what he found was that the further away a galaxy is from Earth, the greater the redshift. So in other words, if a galaxy is farther away from Earth, the increase in wavelength is actually greater. And to further understand Hubble's findings, we need to introduce a little equation, and this is the only equation that you need to know for your cosmology. And this, the V over C equals delta lambda over lambda naught. And here, delta lambda is the change in wavelength, so it is lambda take away lambda naught. And V here represents the velocity of the galaxy, so the galaxy that emits the light waves that we're measuring, relative to the observer. So in this case, it would be Earth, and we have a special name for this velocity. We call it recessional velocity, and that's because the galaxy would be moving away from Earth. It's like receding from Earth. And c, of course, is the speed of light. It's a constant. And lambda is the wavelength of the wave that we're measuring, and lambda naught is the reference wavelength. So this is the equation, the only equation that you need to know for cosmology, and you also need to be able to do calculations with it. But I want to show you how this equation fits into the cosmological redshift and how we can use the equation to understand this. So if we do some rearranging, we will find that the recessional velocity is equal to speed of light times change in wavelength over the reference wavelength. Now, whether the speed of light is constant, the reference wavelength is also constant, so it means that the recessional velocity is actually directly proportional to the change in wavelength. And so let's go back to Hubble's finding. Well, Hubble found that the farther away a galaxy is from Earth, the greater the redshift. That's what he found. And from our equation, we found that the recessional velocity is directly proportional to the change in wavelength. So if we use these two observations and combine them together, then we would be able to conclude that the farther away a galaxy is, the faster it is moving. So in other words, we could say that the greater the distance from Earth, the greater the recessional velocity. So that's what we can conclude from these two observations that we have just previously made. And here's a summary, by the way, for those who might not get it. Further means greater redshift means faster. This comes from the equation. This comes from Hubble's observations. And by combining these two observations, we get this conclusion that further away the galaxy is, the faster it is moving. And this is very important, by the way, and I'll show you some sample questions to know what I mean when I say this is very important. And so from this observation and this observation, we get this conclusion. And this conclusion implies, guys, that galaxies are moving apart from each other. And I'll show you what I mean by this. And by the way, you don't really need to understand it. If you say that this conclusion implies that galaxies are moving apart from each other, you will get a mark in the exam, but I want to help you visualize it, so I will show you how to visualize it later. And because galaxies are moving apart from each other, it implies that the universe must be expanding because galaxies are getting farther apart from each other. So this slide, let's just say, is all you need for cosmological redshift. This is the summary of all the key points that you will need for any question on cosmological redshift. And here is a graph. Now this is the graph that Hubble found. So he plotted the recessional velocity against distance, and if you draw a line of best fit, you can actually see that it's a directly proportional relationship. This is known as Hubble's law. We have V equals h naught d. This is Hubble's constant, and we have the relationship that the recessional velocity is directly proportional to the distance. Now you do not need to know this for your international GCSEs. You do not need to be able to name Hubble's law. You do not need this equation. But if you know this, if you know the fact that the recessional velocity is directly proportional to distance, which you do need to know, you don't necessarily need the equation, you just need to know that they are directly proportional. But if you know the context, I think it helps with remembering. So just keep it in mind. Don't stress out about memorizing the equation. Alright, so let's move on to our summary. This is all you need once again. We would always, so when we encounter any question on cosmological redshift, we would start from light from galaxies, your redshift, and we find that the farther away a galaxy is, the greater the redshift. Greater the redshift, the faster it is moving. How do we know? Because we have this, recessional velocity is directly proportional to the change in wavelength, and therefore we get the relationship. The recessional velocity is directly proportional to the distance, or the farther away the galaxy is, the faster it is moving away from Earth, which implies that galaxies are moving apart from each other, and therefore the universe must be expanding, and this therefore supports the Big Bang theory, because the Big Bang theory states that the universe has been expanding since the Big Bang. And a common misconception is that students often say that redshift of galaxies show that the universe is expanding, because they say that galaxies are moving away from Earth because of the Doppler effect, and therefore the wavelength has increased, and so it must mean that the universe is expanding. And actually that's quite a common misconception. If two galaxies A and B were moving away from Earth at the same recessional velocity, the distance between those two galaxies would remain constant. There's no relative motion between those two galaxies. Yes, they will have moved away from Earth, but the distance between those two galaxies remain constant, and so there's no relative motion between two particular galaxies. And so it is not sufficient to conclude that the universe is expanding. They are only moving away from Earth. It is only when we figure out that a galaxy that is farther away from Earth than another galaxy, it is moving at a greater recessional velocity, that we discover that the distance between those two galaxies also increase. They are moving away from Earth, but at the same time they are also moving apart from each other. And that is how we conclude that the universe is expanding, because all galaxies are moving apart from each other. So I hope this little diagram helps you visualize how that relationship leads to the conclusion that the universe is expanding and how it supports the Big Bang theory. And I think this visualization will really help you answer these questions. And do be mindful of this common misconception that redshift of galaxies prove that the universe is expanding, and no, it is not sufficient to make the conclusion with that. And this is also how we extrapolate. So essentially, because of cosmological redshift, because of the evidence that galaxies are moving apart from each other and that the universe is expanding, we can also look at it in the reverse direction. Okay, so if the universe is expanding like this, what if we look back in time? Well, if the universe is expanding, then at some point in the past, there must have been some time in the past where the universe was just at a single point. Because if it's expanding, it must also go like this. And so this must be the starting point of the universe, and that's the Big Bang theory. The universe must be expanding. It implies the universe began from a single point, and at that point, we call the singularity. You don't really need to know it, but this is how we extrapolate and make predictions, and that's how the Big Bang theory came about, and cosmological redshift supports that. So this is just another perspective, another way of thinking about it. I hope it kind of helps. But yeah, that's pretty much it for cosmological redshift, our first piece of evidence, and it's the big one. Now, let's move on to the second one, which is cosmic microwave background radiation, CMBR. And yeah, it is quite a mouthful, but stick with me, you'll get it. So cosmic microwave background radiation is essentially the remnant of energy that was released during the Big Bang. So during the Big Bang, energy was released in the form of gamma rays. Now gamma rays are really energetic. They are of a high frequency, but their wavelength is very small. But over time, over millions and millions of years, we detect EM waves from all directions. And what we find is that these EM waves are detected as radio waves. And so that means that the wavelength of these waves must have increased over time. So that's our observation. The wavelength of the waves, which are the remnants of energy that was released during the Big Bang, the wavelength has increased. So what are the implications here? Well, the first implication is that, well, the universe must have expanded, because the expansion of the universe must have stretched those waves, causing the wavelength to increase. But the second implication is also that the universe must have cooled down. And to be very honest with you, I don't know the exact physics behind why an increase in wavelength relates to the universe cooling down. But the way I like to remember it is that the cooling down of the universe is because the energy carried by these waves has decreased, and more waves with a higher frequency have more energy, and so this means that waves with a longer wavelength must have less energy. And so because the wavelength has increased, the energy carried by the waves must have decreased, and therefore the universe must have cooled down. And I will admit to you, I do not know if this is the real physics behind it, and you do not actually need to know the real physics behind it. The fact that the universe has cooled down, I actually see this in a lot of mark schemes, and so I think it's important to mention that as well. I don't really know the exact physics. I don't think you do need to know the exact physics either, but just do remember that, the fact that CMBR, the increasing of the wavelength, it has not only the implication of the universe expanding, but it also implies that the universe must have cooled down. So make sure that you do not forget the second implication of CMBR, the increased wavelength. So if we continue making inferences, we will know that the universe must have begun from a single point. Well, that proves the Big Bang theory. But the fact that the universe must have cooled down, it also implies that the universe must have been way hotter in the past. I mean, that's quite an obvious implication, because if it's cool now, then in the past it must have been hot, because it must have cooled down over time. So those are the two implications that we get from cosmic microwave background radiation, and these are quite very important. So if I were to pen any question on CMBR, I would begin by stating that CMBR is detected everywhere, or that it is the same in every direction. And this is important because it makes sure that we are talking about CMBR, because CMBR, it comes from the Big Bang. If it's just random microwaves that are detected in a single direction, then it would be some random waves from a single source from outer space. But that's not what we're talking about. We're talking about CMBR, and CMBR is detected everywhere. It's the same in every direction because it comes from the Big Bang. So when you're writing your response on any CMBR or Big Bang theory question involving CMBR, please make sure to include these words underlined, or something that gives a similar idea, because it's really important to emphasize that you are talking about CMBR. And I would go on and say how the waves initially began as gamma rays, but the wavelength has increased because the universe is expanding, and the increase in wavelength means that the universe is cooling down, and therefore the universe must have been way hotter in the past, and so it must have begun from a single infinitely condensed point. And these 4 points are going to be my go-to writing for any CMBR question, and I will make sure that I don't forget these words that are underlined. Alright, that is the end of today's lesson, but we have got some past year paper practice to do, because the more you practice, the better you'll get at it, and if you do lots and lots of past papers, then you will realize that cosmology questions are actually pretty much the same every year, different wording and slightly different mark schemes, but they almost always come in a similar fashion. So let's take a look at some sample past paper questions. First one is from 2020 June. This is regional paper 2. So let's read the question. Question number 8. The Big Bang theory suggests that the universe is approximately 14 billion years old. Describe the evolution of the universe from the Big Bang until the present day. So when I see a question like this, I would look at the command word, the number of marks, and the focus of the question. So here I see that the command word is describe. We have 3 marks available, and the focus is from the Big Bang until the present day. So I have to talk about how we started, how it has changed during the time. Okay, so here's how I would write my response. I would probably say that the universe began as a single infinitely hot and dense point, which is the beginning, because the question says from the Big Bang. And since the Big Bang until the present day, the universe has been expanding and the universe has been cooling. And that gives me 3 out of 3 marks. And let's take a look at the mark scheme. So here are our 3 points. So essentially, the key technique the key exam technique is to look at your command word, to look at your marks, and to look at your focus, the question's focus, and to pan your response around those three factors, and to make sure that you are fulfilling those three criteria as you write. And the more you practice, your writing will become more concise and you'll get better at it. Right, let's move on to part B. So part B, it says describe the evidence that supports the Big Bang Theory, 4 marks available. Now, from my knowledge of cosmology, I know that there are two pieces of evidence, CMBR and redshift. So I would try to split my response so that I would get 2 marks for CMBR and 2 marks for redshift. So here's how I would write it. CMBR is detected in every direction. Remember, that little phrase is important, or that idea, if you will. It initially began as gamma rays, wavelength increased, so the universe has expanded and cooled over time. So from this part of the response, I intend to get 2 marks. And for the second part, I would say light from galaxies show redshift. So really, I think this would get me a mark for stating that light from galaxies show redshift. The further the galaxy distance, the greater the redshift, the greater the redshift, the greater the recessional velocity, and this relationship implies that the universe is expanding. So that's 2 marks. Now here, if you look at the wording is actually very concise, it's very straight to the point. So you will get 1 mark for saying that CMBR comes from all directions, and that the wavelength has increased. So really, I do get 2 marks for my CMB response, and I get a mark for redshift, and I get a lot of marks. Sorry, 2 marks, 2 more marks. So I get 3 marks from redshift and 2 marks from CMBR, so you have 5 marks. So as you can see, it's very concise, it's very succinct, but it ticks all the mark points on the mark scheme. And MP1 to MP6, these mark points get repeated almost every time these kind of questions come up. The phrasing, of course, does change. So yeah, this is a good mark scheme to note, and maybe you might want to memorize off the mark scheme. So this is a good one. But we will take a look at another question from another year. This time we're looking at 2023 January, paper 2 R again, question 8, and as you can notice, it only appears on paper 2 because it's a triple science topic. Let's take a look at this particular question. So it says, between 1929 and 1931, physicists Hubble and Humason investigated the redshift of light from galaxies at different distances from the Earth. The distance unit they used is the megaparsec. One thing that I would like to point out is that the megaparsec is not a unit that you need to know for your specification, but Edexcel really like putting let's say physics content or whatever exam you're doing, they really like putting content from outside the specification. And some students, when they see stuff like this, they get shocked, they start to panic. And so my advice is, do not panic when you see things that you've not seen before, when you see content that's outside the specification. More often than not, they can't really ask you what that is about unless they give sufficient information to be able to solve that question for students who will have knowledge within the specification. So do not panic. And let's take a look at question part A. It says describe what is meant by the term redshift. So as you can see, first question, nothing to do with the megaparsec, so nothing to be scared of, right? So let's answer the question. It's a describe question and we have 2 marks. So it's going to be quite a straightforward question. So what is redshift? How do we understand redshift? Well, redshift is essentially just the increase in wavelength of light waves. Why? Well, that increases because the source or a galaxy is moving away from us. So that's it. The increase in wavelength because the galaxy is moving away from us. Quite simple, 2 marks, done. Let's now move on to part B. Now part B is a graph question. Now they already have the axes done and the plots for us. So all we need to do is draw a circle to show the anomalous data point. Now the anomalous point is the data point that is an outlier. It does not fit the pattern. So I will try and roughly draw a line of best fit. And I can already see that this point is very off. So this would be the point that I'm circling. And as for my line of best fit, I would use a ruler and I will use a ruler and try to make sure that my line of best fit passes through as many points as possible. Always use a ruler when you are drawing straight lines in your science exams or your maths exams. And I think that should give us 2 easy marks. Right, so far we have 4 marks already banked. Let's take a look at question number 3. Now question number 3 is the calculation question. So let's read. The reference wavelength of the light used in this investigation is 660 nanometers. Use information from the graph, okay, to determine the velocity of the galaxy at a distance of 0.75 megaparsecs, and the speed of light is 300,000 kilometers per second. So now we see the megaparsec in our question, but we do not need to be scared because they do give us sufficient information. They said use the information from the graph. So what I would do is I would flip back to my graph. I will look at 0.75 megaparsecs, which should be right here, and I will look for the corresponding change in wavelength value, and it appears to be 0.03 nanometers. I think exactly there. So what I would do is I would write delta lambda equals 0.03 nanometers. And I will look back at my questions and I would write down the variables that I've been given. So let's say the reference wavelength of the light used in this investigation is 660 nanometers. Well, that's a lambda naught, and they gave it as 660 nanometers. Okay, and we have C, which is 3 times 10 to the 5th power kilometers per second. So using our equation, V over C equals delta lambda over lambda naught. Well, if we look at the equation, we already know C, we already know change in wavelength, we already know the reference wavelength, and so we can find what we need, which is the velocity of the galaxy. So rearrange, we will multiply both sides with C, and we would substitute. So this would be 3 times 10 to the 5th power times the delta lambda would be 0.03 over 660 nanometers. And if I punch that into my calculator, I should get 13.6 kilometers per second, 2, 3 significant figures. So this would be my answer. Let's take a look at the marking. And yes, 13.6 is indeed allowed. So you get 1 mark for reading off the graph, another mark for substitution, and another mark for correct evaluation of the answer. And that's the calculation, and this is the style of the question that you get for equations, for using the equation V is equal to, sorry, V over C is equal to delta lambda over lambda naught. So this is a very common question type that you'll see for cosmology when it comes to calculations. Alright, last part question. It says, explain why the graph from Hubble's investigation provides evidence for the expansion of the universe. So going back to the graph, how does this relationship provide evidence that the universe is expanding? Well, it's essentially what we know. As the distance increases, the change in wavelength also increases. So that's the first thing that I'm going to write about. As the distance increases, the change in wavelength increases, and I might even say that the change in wavelength is proportional to distance, but I think it's safer to say that as the distance increases, the change in wavelength increases. And from the equation, we would know that the recessional velocity is directly proportional to the change in wavelength. So as the change in wavelength increases, the recessional velocity is increasing, and so that relationship implies that the universe is expanding. And I've already shown you how to visualize it, so I hope you get it. So for this 2-mark question, I will probably write something like this. I will probably show that the increase in wavelength increases with distance, and then the recessional velocity increases with distance. So here's the relationship, and that relationship implies, so that relationship, from that relationship we can conclude that galaxies are moving away from each other, which implies that the universe is expanding, but that is the already given in the stem of the question, so we just need to explain these 2 observations and what they show us. thank you for watching the video until the end, and good luck with your examinations, especially October, November 2025 candidates. And we will be having more videos like this coming soon to the channel. We will have videos like this for your GCSE sciences, including human biology. So Edexcel International GCSE Science will have it for human biology and other sciences, and we'll also have videos for your maths, especially for specification B mathematics, and also maybe for further pure mathematics, and maybe I don't know if I'm in the mood for it, I'll do some English language as well. So stay tuned, subscribe to the channel if you're interested, and I'll see you guys in the next one. Peace.